Good morning, dear students. My name is Ferhan Mazher, and the subject today we are studying is Cambridge O-Levels Physics 5054. Today we are going to work on paper 4. We call it Alternative to Practical, or we call it ATP. And in this video, we are going to attempt a specimen paper which the Cambridge has issued for the examination, which are starting from the June 2023. So there is a little change now. The paper 4 will be of 40 marks. Previously it was of 30 marks. Now it will be of 40 marks, and this is the one specimen paper which is available on the Cambridge website. And in the June, the paper will be on this pattern. So today in this video, I'm going to present to you the solution of this paper, and I will try my best to explain all the concepts and give you an idea how to write these answers. So let's start today's paper. Okay, so on your screen, the paper is showing up. This is specimen paper 4 for the Cambridge O-Levels Physics 5054. And this is for the examinations which are from 2023. Important thing is this, the total marks for this paper is 40. So let's start today's paper. So here we go. A student investigates the effect of varying the amount of light reaching a light-dependent resistor, LDR. She sets up the apparatus as shown in the figure 1.1. So here you can see we have a resistor, a voltmeter, a power supply switch, and we have connected it with the LDR. LDR is a resistance. A resistor whose resistance changes with the amount of light falling on it. If the intensity of the light will increase, the resistance of the LDR will decrease. If the intensity of the light falling on the LDR will decrease, the resistance will increase. So this LDR, with the help of some adhesive putty, we have been attached with the side of a beaker. The beaker is transparent and it is filled with the water. And in this water, we have mixed some color to change the light which will be reaching the LDR. And here we have a light source. So this light source passing through this beaker will reach this LDR. Due to that light, the resistance of that LDR will change. When that resistance will change, the reading on the voltmeter will also change. So he says that in the figure 1.2 shows the readings on the voltmeter when the light source is turned on and the switch is closed. Record the reading on the voltmeter on the answer line and in the first row of the table 1.1 on the page number 4. So what is the reading on the voltmeter? This is right now, I can increase the size so you can see it more clearly. So this is 3, this is 4, so this is 3.2, 3.4, 3.6, 3.8, and 4. So this reading is right now 3.2 volt. So the reading is 3.2 volt. So you can write it 3.2 volt. So my answer is 3.2 volt. The answer is right. So here we go. So then they say the student uses a syringe to add 2 centimeter cube of a colored liquid to the water in the beaker and stirs the mixture. Explain why the student must stir the two liquids together. So what the student do, he adds in this water 2 centimeter cube of a colored water to change the color of this water. And before doing this experiment, what he do, he stirred this water. Why he stirred this water? To make sure that the color is uniform throughout the body of the liquid. So our answer is, so the color of the liquid is uniform throughout the water. This is what our suggestion is. He says anyone from, so that the color is evenly distributed so that the reading on the voltmeter is repeatable. So you can repeat the reading. Okay. So this is my answer. Okay, so we are going to the next part. The next question coming up on your screen is the B part. He says, the reading on the voltmeter was 3.2. I think 3.2. It was the reading was 3.2. Yes, the reading is 3.2. Okay, so we are going to write that value here in this table. So let me show you this table. The student continues to add 2 centimeter cube of the colored liquid to the water at a time, recording each new voltmeter reading in the table 1.1. So the volume of the colored liquid when there is no colored liquid. So here you have to note it down. So our reading is 3.2. So what we will do, 3.2. Okay. So my reading there is 3.2. Okay. So in that table you have added, that was asked in the previous question. Okay, so we have written here 3.2. Then we will go on the figure 1.3, plot a graph of the voltmeter reading against the volume of the colored liquid. Draw the best fit curve. Okay, so this is that volume of the colored liquid, centimeter cube, voltmeter reading in volts. So this is the table, and here we have here we have how much reading? 3.2. So the V is on the x-axis, and it is going from 0 to, this V means the volume. It is going from 0 to 12. Okay, so we can represent here, yes, on the x-axis, it is already graduated. It has already has been labeled. The y-axis, the voltmeter reading is in volts. This is 3.2. The smallest reading is 1.4. So let me show you. I have done this, and here we go. So I will label the graph, and you can see here. So 2, 4, 6, 8, 10, 12. This is the volume of the colored liquid. Here is the voltmeter reading, which is in volts. And I have not started it from the 0. I've started with 1 because my least value is 1.4. So that's why I will do that. And it's 1 here, and 2 here, and 3 here, and 4 here. So this is also the 2 small squares on the y-axis represents 0.1. 0.1. Okay. Now we will enter the values. So the values are, this is my table, and this table you can see at 0 you have 3.2 reading. At 0 you will put a dot of 3.2. You go 4 small squares above the 3 because 2 small square represents 0.1. So 3.2 will be 4 small square. You go above this. So this is what you will do. Then we will have at 2 you will have 2.4. At 2 you will have 2.4. Put this dot. Then you will have at 4 you have 2.2. At 4 we will have 2.2. I will put this dot. And at 6 you have 1.8. At 6 1.8. This is the dot. And so okay, so then at 8 you will have 1.6. At 8 you have 1.6. And and at 6 you have 1.8. At 8 1.6. At 10 you have 1.5. And at 12 you have 1.4. At 10 you have 1.5, which is this 1.5. This is the dot. And at 12 you have 1.4. This is the dot. Okay, so then I will join them with the curve of the best fit. This is the curve of the best fit. You see, this point and this point has been left. So the curve is going between them. Okay, so this is the curve of the best fit. And then their question is, plot figure 1.3, plot a graph of the voltmeter reading against the volume of the colored liquid. Draw the best fit curve. We are done with that. Okay, so question number 1C, first part, draw a tangent to the curve at 5 centimeter cube. So at 5 centimeter cube, which is here, you have to draw a tangent to this curve. So I have drawn this tangent. You can see this tangent. And then their question is, calculate the gradient of the tangent. Show your working and indicate on the graph the values that you have used. Okay, So I am going to use this point. I will take 2 points on that tangent line. So I'm going to use this point whose coordinates are 0, 2.65, and I'm going to use this point whose coordinates are 10, 1.2. And by using them, I will find out the gradient of this straight line, which is tangent to that curve at x equals to 5. So you know the gradient formula is in your mathematics you have studied. The gradient can be calculated by the formula y2 minus y1 divided by x2 minus x1. This is your mathematics. So let me show you. I have done this, and here we go. So the gradient will be how much? I'm taking these points 0, 2.65 and 10, 1.2. The gradient will be y2 minus y1 divided by x2 minus x1. It will be 1.2 minus 2.65 divided by 10 minus 0. It will be minus 1.45 divided by 10. That will be minus 0.145. That is minus 0.145. So this is the gradient. So let me check. Yeah. It says, describe one precaution taken to ensure that the reading from a voltmeter is accurate. Okay. So these are the answers of from the marking scheme, you can see. And let me, okay, now it's good. Anyone from, okay, so all values in table plotted correctly to within the 1/2 small square, smooth curved line of the best fit with even distribution of points either side, and gradient remains negative. Tangent at 5 centimeter cube, 2 correct sets of x and y values from the candidate's line and separated by at least 5 centimeter along the tangent line drawn by candidate. Values substituted by delta v by delta x and evaluated. Anyone from, this is the 1D part, check for 0 error, tap the meter in case the needle sticks. So their next question is, they're asking us to describe one precautions taken to ensure that the reading from a voltmeter is accurate. Let me show you the question. Okay, so it's a 1-mark question. Describe one precaution taken to ensure that the readings from a voltmeter is accurate. If you want to take the reading from a voltmeter accurately, you should, first of all, before using the voltmeter, you should check if there are 0 errors in that voltmeter or not. If there are 0 errors in the voltmeter, then after taking the reading from the voltmeter, you have to do the correction for that 0 error. So this is my answer. And let me just show you my written. And before using voltmeter, check 0 error. If there is 0 error, then make that correction in the reading. This is my answer. Then he says, another student performs the same experiment. He calculates a gradient which is slightly different to the value you obtained in the second part. So just 2 variables that are difficult to control that may result in different gradients. You see, the 2 things, because the reading on the voltmeter depends upon the source of the light, the amount of light which is reaching the LDR. So it's difficult, one thing, to control exactly the amount of light, the intensity of the light which is falling on the LDR. And another thing is very a little difficult to control is the color of that water through which the light passes and falls on that LDR, because you know the color which you are using to control its consistency, it is difficult because you buy the color from a market, and obviously when you mix the color to the people who works with the color, they know to exactly get the same color again and again. It is a very difficult process. If you have gone sometimes to get your cars repainted, or you go to a denter painter, so when they match the color with the color of the car, it takes them a lot of time. They do mixing again and again, hit and trial, and then they get the same color. So to get the same color each time, it's difficult. So these are the 2 reasons which I believe. Intensity of the light may change. So to keep intensity of the light same is difficult. And another thing is difficult is consistency of the color which you are using, and the color of the water is difficult to keep the same. Okay, so these are my answers. So let's have a look at the marking scheme. Check for the zero error, tap the meter in the case the needle sticks. If the pointer of the voltmeter gets stuck, just give it a little tap like this, and it will free that pointer of the voltmeter. And E part is any two from level of the background light is difficult to control. The type, mix, or consistency of the colored liquid, distance between the light source and the LDR, how much water the colored liquid is mixed with. So these are the answers given in the marking scheme. I hope you will be able to write better answers. And these are my answers. So question number 1 is done. Okay, so we will go to the next question. And the next question is, he says, let me, there is a little issue with the, okay, so where we should move it. We can move it here. Okay, so I'm going to the next question, and the next question is on your screen. This is question number 2. A student investigates the effect of the two lenses on the size of a shadow. He sets up the apparatus as shown in the figure 2.1. So let me explain to you. Here we have a stand. This is the base of that stand. This is the counterweight so that the stand do not topple. Here in this clamp, we are holding a lamp, and this lamp is connected with a power supply. Here in this clamp, we are holding a lens. It's a convex lens, and here we have put a clay, a small piece of modeling clay. And when this lamp is switched on, the shadow of this clay will be formed on this paper here. Here we have put a graph paper. You know, on the graph papers, we have those grids. So from the graph paper, I want to measure what is the diameter of this shadow. Okay, so here we have lamp, here we have lens. On the lens, we have a modeling clay. So when this lamp is switched on, the shadow of this clay is formed on this graph paper, which is on the bench. The height of this lamp from the bench is Z. The height, the distance between the lamp and the lens is X, and the distance between the lens and the bench is Y. So I hope you understand this diagram. He says the student uses a small lamp connected to a 3.3 volt power supply. Okay. He attaches the lamp, holding the lamp to the highest position on the stand. In this position, the distance Z between the lamp and the bench is 56.5 centimeters. So this distance Z is 56.5 centimeter. He places one of the glass lenses in the jaws of a clamp at a distance of X equals to 20 centimeter below the lamp. So this lens is 20 centimeter below the lamp. This X value is 20 centimeter. Describe two precautions. Precautions to take to ensure the apparatus is set up safely. Set up safely. Okay, so let me tell you two precautions. Can you see this clamp? It's holding this lamp. This lamp has electricity in it, and this lamp is made up of glass. And this clamp is holding that lamp. So when you tighten the clamp, and make sure you do it gently, slowly, because you know if you tighten it too quickly, the clamp that will crush the glass of that bulb. This is one precaution. The other precaution is, can you see that this whole thing? The weight, the lens is on the right side of this stand, and this lamp is also on the right side. So you have to put a counterweight here on the left side of the base of the stand, so that the chances that due to the weight of these two, the stand might topple to the right. To avoid this, you put a counterweight on the left side of the base so that the stand do not topple during the experiment. So these are the two precautions which I suppose we have. Okay, so my answers are the clamp holding should be tightened slowly. The clamp holding, here I should have written lamp. The clamp holding the, I want to write here, the clamp holding the lamp should be tightened slowly and softly, because clamp can break glass of lamp. Okay, the second place is counterweight place. You can say the place counterweight on left side of the base of stand to make sure that stand might not topple to the right. These are my answers. So let's have a look at the marking scheme. He says weight to prevent stand toppling, supply voltage not exceeding rating of the lamp. The lamp is through 3 volt. Do not connect it with some higher voltage. That will cause the lamp to fuse. Lens clamped securely because glass can break. Apparatus away from edge of the bench so the apparatus do not fall on the floor. Leads to the supply are pushed out of the way. And moment due to lamp and or lens is small reduces risk of toppling. So you should try to keep the moment of the lamp and lens smaller. So the length of the clamp should be smaller. So because if the length of the clamps which are holding the lamp and the lens, if their length becomes longer, the moment of the lamp and that lens will increase and it will topple to the right side because the moments will become larger. So these are the answers from the marking scheme. This is my answer. Okay, so we are going to the next question, the next part, I mean. And that is question number 2B part. The student switches on the lamp. The lamp light and the modeling clay produce a shadow on the graph paper. He holds a second lens under the lamp. When this lens is touching the lamp, the diameter D of the shadow of the modeling clay on the graph paper is 2 millimeter. The student moves the second lens down towards the clamped lens. He observes the change in the diameter of that shadow. He records his observations on as shown in the figure 2.2. So D decreases as the second lens moves away from the lamp, sorry. The shadow of the D disappears from the view as x is equals to 9 centimeter. At x equals to 10 centimeter, it appears again and increases in size. When the second lens is touching the clamped lens, D is about 6 times bigger than it was at 0 centimeter. Okay. So he says use the student's observations to sketch a graph on the figure 2.3 showing how D changes with increasing. Okay. So what I will do, I will write here, take a point here. So 2, 3, 4, 5, 6. So 7, 8, 9, 10, 11, 12. Okay. So suppose suppose this is 2, 4, 6, 8, 10, 12. This will be 12. Okay. So when it's 0, the diameter of the shadow is 2. When it's 9, at 10 it reappears again, and at 20 it is 12. It is 12. At 20 it is 12. So join it with the straight line here. Then it goes like this. and then it goes like this. Okay, so this is how you will draw this graph. Okay, this is coming from here. D decreases as the second lens moves away from the lamp. The shadow of the D appears from view, disappears from the view at x equals to 9 centimeter. At x equals to 10 centimeter appears again and increases in size. When the second lens is touching the clamp lens, D is about 6 times bigger than it was at 0 centimeter. So I have drawn this. It's a very little tricky thing. So I wrote it here. So I wrote here 1, 2, 3, 4, 5, 6, 7, 8. So I went little out of that. So if this is 2, at 0 you have 2, at 9 you have no shadow, at 10 the shadow appears again, and at 20 you have 12. 6 times more than 2. So join it with a straight line, then like this, then like this. I have drawn this graph again because I went out of that graph paper. So you can see this. Okay. So on the hard copy of your paper, I believe make this shape. Okay. 12 at 0 you have 2, at 9 you have 0, at 10 0, and at 20 you have 12 really. This is the shape which you will get. I hope you understand, and here we go. So this is the marking scheme. I have already checked my answer with the marking scheme. So then their question is, the student removes the modeling clay from the clamped lens. He keeps the lamp at the top of the stand. He can see an image of the lamp on the graph paper on the bench. He adjusts the position of the clamped lens until the image is as small and bright as possible. He finds that he cannot position the clamped lens so that the image seen on the graph paper is in focus. The image is as small and bright as possible when x is equal to 27.6 centimeter. Calculate y. Okay. So the from that figure I can tell you the y. From this figure I can tell you the y is equals to x minus z. This y, if I know this z, that is 56.5, and I know the x value, so I can find the y. The y will be z. The y will be z minus x, and that will be 56.5. Y value is 56.5 minus the x value he just told us, that's 27.6, and that will be 28.9. So the y value is 28.9. Then he says, a student suggests that the focal length f of the lens can be calculated by using the equation. F is equals to xy divided by x plus y. This is the formula I just given. You have to put the value of the x and the y. The x value is this and the y value is this. Just put these values here, and I have done that. 27.6 multiplied 28.9 divided by, and in the denominator I will write 27.6 plus 28.9, and you will get, when you enter these values in your calculator, you get 14.1 centimeter. 14.1 centimeter. So marking scheme is showing up on your screen, and you know that it's 14.1 centimeter. So our answers are right. Okay. He says, very simple question, describe two. We are sorry here. Question number 2, it's C part, first portion is done, second portion is done. Now we are on the question number 2, it's D part, first portion. State why the arrangement of the apparatus shown in the figure 2.1 cannot be used to accurately determine the focal length of the f. You see, he said that the lens, the image is not focused. Okay, cannot be positioned the clamps of the lens image seen on the. Okay, so the image is still not in focus. Okay, So to get a clear image, the distance between the graph paper and that that lens should increase. Okay. So that basically the distance between the lamp and the graph paper should increase. Then we might be able to get a very sharp image of that lens. So because to get a sharp, I read here sharp. Here this means it's sharp. Sharp image, the distance between lamp and the paper need to be increased. You cannot get a sharp image. The lamp and the paper needs to be further apart to get a sharp image. So the distance between the lamp and the paper should increase to get a sharp image. Suggest, then the question is to suggest how the arrangement of the apparatus can be changed in order to accurately determine the focal length of the clamp lens. My suggestion is that we should use a stand which is longer so that the distance between the lamp and the paper can be increased. Use a larger rod so that the distance between the lamp and the paper can be increased to get a sharp image of the, this is not clay, of the lens. Okay, so remember I just wrote here clay. The clay has been removed. So okay, so let me show you some valid practical suggestions to increase the distance between the lamp and a paper. For example, use a longer rod, raise the stand. So you can also put something under this stand. Let me show you that. He gave us a suggestion that put something under. Let me show you. Where is that diagram? Can you see that? The graph paper is on the bench. So if you do not have a larger stand, so what you can do, you can bring more, like for example, bring 4 dictionaries and put the 4 dictionaries on the bench, and then on top of those 4 dictionaries, put this the stand, so the distance between the lamp and the graph paper, that will increase. So I hope you understand what I'm saying. I hope you understand this whole story also, and that's it. Okay, so let's check the marking scheme. I think yeah, we have already checked this marking scheme. So we are going to the next question, and that is question number 3. He says, a student investigates the question number 3 we are studying now. A student investigates the oscillation of masses attached to a meter rule. So they will take a meter rule, they put a mass on it, and then they make the meter rule vibrate. From here, they are holding the meter rule, so the meter rule will vibrate. So they will note down the time period for that vibration. She attaches two 100-gram masses to the end of the meter rule. One meter rule is like 100 centimeter long. The diameter of the width of one of the masses are shown in the figure 3.1. He says on the figure 3.1, measure means to, by using a meter rule, you have to measure it. The length, D, and the W. So put a meter rule here, check how much is this, and put a meter rule here, check how much is this. I think you can measure them in centimeters, or if you want to do that, you can measure it in millimeters. So I have measured it, and the diameter is 3.9 centimeter, and the width or the thickness, that is 1.1 centimeter. So that's question number 3 showing up on your screen. So my answers are these. Okay. Then we have, he says the student sticks the pair of the matches together and secures them to the end of the meter rule by using an adhesive putty. Part of the scale at the end of the rule is covered by the masses as shown in the figure 3.1. Describe a method to determine the position of the center of the mass on the meter rule. So the diameter is 3.9, and you see this end, this is starting from the 0. So here you have 0, and up till here is the diameter. So the center of the mass will be 0 plus half of the diameter, which is radius. So that will tell you the position of the center of the mass on the meter rule. Zero, why I'm saying zero? Because here on the meter rule you have zero. And then add the radius and you will come to the position on the meter rule where there is the center of the mass of these two coins or these two cylinders or these two masses. So this is how you can describe a method to determine the position of the center of masses on the meter rule. That's the first part. My answer is 0 plus half the diameter of the cylinder or that mass. So this is my answer. So you can check this as right. And then it says suggest why student does not attach the masses to the lower side of the meter rule. If you put this at the lower side of the meter rule and you use the adhesive putty, so that will not be able to hold the mass attached at the bottom side of that meter rule, and the masses will fall on the ground. So it becomes the masses will fall to the ground. Simple. Adhesive putty will not be able to hold the cylinder mass attached to the lower side of the meter rule. So mass will fall down. Masses are more likely to become detached, or adhesive not strong enough to hold them. That is what we have written. Okay, then we have, this is question number 3, and it's B part, and its third portion. He says, the other end of the meter rule is attached to the bench as shown in the figure 3.3. The edge of the bench is at 10 centimeter mark on the meter rule, and you see, determine the distance L along the meter rule, along the rule from the edge of the bench to the point on the rule directly below the center of the mass. Use your values. Okay, so here, this is this point. This is 10 centimeter. Okay, so this rule is total 100 centimeter long. So 10 centimeter is here. The center of the mass will be here, and I know this distance, that is the radius of that mass. We just measured that diameter, that was 3.9 something. So just divide it with the 2. So from 100 subtract 10 and the radius, and you will get the distance from this to this point. Okay, so show your working. He said determine the distance L along the rule. Let me read. He says determine the distance capital L along the rule from the edge of the bench to the point on the rule directly below the center of the masses. Use your value of the D from the part A. Show your working. Okay, so it's a 2 marks question. So here we go. So the distance between the edge of the bench and the center of the mass will be 100 minus 10 minus 1.95. What is 1.95? That is the radius of that mass. So it will be 90 minus 1.95, and that will be 88.05. So when you round it off to the nearest millimeter, it will be 88.1 centimeter. So I hope you understand this. 88.1 centimeter. Okay, so then we have, he says the student, then they say the student lifts the free end of the meter rule until the rule is approximately horizontal. She then releases the meter rule and observes the masses oscillating. So she lifts the meter rule like this, she lifts it and then let it go. So the meter rule will vibrate like this, and she observes the time taken for 20 oscillations of that meter rule. And one time she noted that it takes 10.56 seconds. Then she noted that it takes 10.51 seconds. Then their question is determine the time small t for one oscillation. Show your working. So the method is, first of all, find the average time taken for 20 oscillations, then divide that average time with the 20, you get the time. So add these two times together and divide with the 2. So you get the average time taken for 20 oscillations. That will be 10.535. Then divide it with the 20 because this is the average time for 20 oscillations. So you get the time for one oscillation. So that will be 10.535 divided by 20. When you do it on the calculator, it will be 0.52675, which when you round it off, it is 0.53 seconds. So the time taken for one oscillation is 0.53 seconds, which is right. The marking scheme is showing up on your screen. You can pause the video and you can take your time with this marking scheme. Okay, then they say, the student repeats, that's the second part of the question number 3C, second part. He says the student repeats her experiment for 4 more values of L by moving the masses along the top surface of the meter rule. In the table 3.1, record your value of L from the B third part and your value of the T from C first part, and add an appropriate unit of the heading. The length is in centimeters, the time is in seconds, and here we will write the L value and the T value. We have done that. And here we go, the L value is 88.1 centimeter and the time for one oscillation is 0.53 seconds. So this is the marking scheme showing up. So then their question is, on the grid, plot a graph of the T on the y-axis against L. So the T will be on the y-axis and the L will be on the x-axis. You do not need to start your graph from the origin. Draw. Okay, so for this table, L will be on the x-axis, the T will be on the y-axis. So I'm going to draw a graph. So I have done that. Let me show you. Oh my God, this graph is huge. So on the x-axis, I have written here 30, 40, 50, 60, 70, 80, 90, 100, 110. The x value is changing, going from, I think, 40 to 100. Okay. 40 to 90, I think, 88, sorry. And the T values, that's in centimeter. This is called labeling. It's very important. The T value in seconds, it is going from, so it's 0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.55, and this is 0.6. And then I will plot the points. So how you will plot the points? You see here we have that table at 88.1. The reading is how much? At 88.1. So no, but it's better. From at 40, you have 0.22. So at 40, I have 0.22. I put a dot here. At 50, it's 0.27. At 50, you have 0.27. And at 70, you have 0.42. So at 70, you have 0.42. Put this dot. Okay, then at 80, you have 0.46. And at 80, you have 0.46. This is the dot. And at 88.1, you have, I think, 0.56. This is the reading. I think this is the table. 0.53, sorry, I said 0.56. So once you have plotted those points, then you will draw a line of the best fit. And here you can see these are the points. So I have drawn a straight line passing through these points such a way that the number of the points above this line and number of the points below this line, they are same. So this is the line of the best fit. I hope you understand. And then their question is, okay, we are done with this. It's a 4 marks part. The fourth part is, use the graph to estimate the value of the T when the L is 60. So when the L is 60, from here, go to your line of best fit, check what is this reading. This is 0.345, I think. And I have written this answer. So this reading will be 0.345 from the graph. I can tell you, let me say this is 60. So how much is this reading? This is 0.345. So our answers are right. This is the marking scheme. Okay. Then their question is, the question is over. Now we are going to the next question. The next question coming up on your screen is question number 4. He says a student places a small metal container inside a larger metal container, as shown in the figure 4.1. There is an air gap between the two containers. The student investigates the effect of the size of the air gap on the rate of the cooling of the hot water. So here we have a smaller container. It is filled with hot water, and it is placed inside a larger container, in the middle of the larger container. So this is the air gap between the walls of both the containers, and we note down how much time, how we want to investigate that the rate of the cooling. Okay, so their question is plan an experiment to investigate the effect of the size of the air gap between the small metal container and a larger metal container on the rate of the cooling of the hot water. The following apparatus is available: a small metal container, a number of metal containers of different diameters are larger than the small container, a thermometer, a stopwatch, a measuring cylinder, a supply of hot water. Their question is, you can also use other apparatus and materials that are usually available in a school laboratory. You are not required to do this investigation. In your plan, you should explain briefly how to carry out the investigation, state the key variables to control, draw a table or tables with column headings to show how to display your readings. You are not required to enter any readings in the table. Explain how to use your readings to reach a conclusion. A diagram is not required, but you may draw one if it helps your explanation. Okay, so what we will do, you see, you take a small container and you take a large container. Place the small container in the larger container, and place take the hot water and put it in a measuring cylinder. So just note down a specific, for example, you take 300 centimeter cube of the hot water. For example, you take 200 centimeter. So every time you will take the same volume of the hot water. So pour that into this small container and put thermometer in it and wait. For example, the water is 88 degrees centigrade, and let it come down. And when the temperature is 70, start the stopwatch and note down how much time it takes to cool down to 60 degrees centigrade. So now the temperature drop is from 70 to 60, and on the stopwatch you have noted down how much time it takes. Then change the water. Now take a bigger container, the bigger container than the container which you have used previously, the outer container, a container which is more than that container, bigger than that container, and place that small metal container inside that, now the larger container, and again pour same volume of water in that small metal container. And when the temperature, with the help of the thermometer, note down the temperature. When the temperature becomes 70, start the stopwatch. When the temperature becomes 60, stop the stopwatch. Why I'm telling you 70 and 60? Because I want the initial and the final temperature same. I want to measure every time the same temperature, some same temperature drop, and I am noting down how much time it takes. Okay, so the air gap, you see, this is how you will do your investigation. This is what you will be observing. Okay, and the things which you have to control, variables to control, you see, the amount of water each time should be same, and the initial temperature from where you start your stopwatch and the final temperature at which you stop your stopwatch, that should be same, and the temperature of the laboratory or the room temperature should be same. Okay, so draw a table. Okay, so the table, in the table should have air gaps, and then you should have the change in temperature, and then you should have the the time taken. So then how you will have the conclusion? If by changing the air gap which will take less time to change the same amount of temperature, the air gap which will take the less time for that change in the temperature, in that air gap, the cooling rate is the fastest. So this is how you will design these experiments according to these given parameters. So let me show you. I have written this, and let me show you. So I think we have missed the D part of the previous question. When L will be less than 40 centimeter, value of the T will be very short, and the frequency of the vibration will be high. And when the L is 60 centimeter, T is 0.345. I hope I have not missed it, but I think I missed it, the last part. So here is the marking scheme. First of all, let me read my answer. So here we go. Put a specific volume of hot water in smaller container and place smaller container in a larger container. Place a thermometer in a smaller container when temperature is 70, because it will be hot. For example, it will be 85 degrees centigrade hot water. So wait, when the temperature of the hot water becomes 70, then start your stopwatch. So when the temperature is 70 degrees centigrade, start stopwatch, and when temperature is 60 degrees centigrade, stop the stopwatch. Repeat experiment by using same smaller container but a more larger container for the outside. By doing this, the gap between the smaller container wall and the larger container wall is increased. The air gap is increased. So do the same observation each time. Volume of hot water should be same each time. Note down time required to drop the temperature of the hot water from 70 to 60, means the change in temperature is kept constant. Each time room temperature should be same. Following table can be used to note down observations: the air gap in centimeters, temperature drop in degrees centigrade, and the time taken in seconds. The air gap that takes less time for same change in temperature as compared to the other air gap has the greatest cooling rate. This is my conclusion. So this is coming up on your screen. You can pause the video here and you can note down this answer. Then stop the video here and note down the answer. So hot water in small metal can, time taken for temperature to drop. Use of at least 3 larger outer containers. Yes, do it 3 times at least. Each time change, make the container bigger, then the outer container should be larger and more bigger container. Controls: same volume of the hot water, same room temperature, same starting temperature of the water. Table with the clear columns of the air gap, temperature change, time taken to match the method with appropriate units. Conclusion: the air gap that causes the greatest change in temperature. This is one. But the way we wrote it, it is has shortest time, shows greater rate of cooling. Or you can say plot temperature against the time and steepest gradient shows the greater rate of the cooling. So we have reached the end of this paper. So this is the answer which I have written, and let me show you. So you can pause the video, and you can pause the video, and here we go. You can pause the video, and you can pause the video. So my dear students, we have reached the end of this paper. And today in this paper, we have done the specimen paper 4, alternative to practical, or we call it the ATP paper. This is a specimen paper for the examination from the 2023. In this video, I have presented you the solution of this paper. I have tried my best to write the best answers possible. But I believe that my students, they can write a much better answer. You have one answer suggested by me. You also have the marking scheme, and you also have your own teachers. You can discuss with them, and you can write better answers. Uh, if you think that this video has helped you to practice the ATP paper, please like this video. Also share the link of this video onto your Facebook, onto your Twitter account, and onto your Instagram. Because when you do this, this helps me to promote my channel. I think it's a great blessing for me that I can make these videos and I can touch the life of so many students around the globe. Thank you very much for watching these videos. Have a good day. God bless you all.